All right. Share. Okay, let's start. So in today's lecture, we're going to talk about the material jetting and powder bed process. And they're a little bit similar because they all utilize the powder as the building material, but there are some differences, especially for how to bind the powder particle together. It has very distinct differences there, features there, all right? And so this is an illustration for the printing system of the material jetting systems. As you can see, basically here, let me show the laser. So you have this liquid adhesive supply devices. Basically, it spread the binder agent, usually some glue there, to bind all the material particle together. And also you can see there's a there's a mechanism to lower the printing platform and by the amount of the thickness, layer thickness. At the same time, there's another tank of the powder bed, and there's a leveling roller to spread the powder onto to cover the previous layer, such that you could have more material to work on. So that is the kind of basic concept for this kind of material jetting process. It's quite similar to the 2D jetting, but you have this D movement such that you could build one layer, upon another one, right? And as I mentioned, you can see this kind of a technology is kind of get inspired from the 2D printing, right? So at first we have the 2D print invented, and then some researchers expand the idea of 2D printing by introducing more features like some electronics, conductive wires, electronics ink, and optical material, and so on and so forth, onto this 2D printing. And then they came up to the idea with the 3D printing. Basically, they build one layer upon another one. And there are a lot of different process as we introduced. There's some direct part printing, like they used liquid resin, wax, metal, powder, or so on and so forth as the either printing material or the binding agent. Or they use the glue to bind all the powder particles together. And let's have a very brief review on those historical development of such kind of printing approaches. And as you can see, there are some work. Basically, they use the wax to build up the model together. Wax is very easy to melt and to spread by the very simple mechanisms, right? And for the 3D systems, besides the SLA printer, stereolithography printer, they also have those jetting based, right? They develop a wax based machine, and also they have those binder jetting machines as well. And also another very, I would say, main player is called ZCOP. That is a main supplier for those binding 3D printers. And they are developed, actually they initiate the work at MIT and then licensed to a commercial company like ZCOP and X1 and so on and so forth. Actually, this X1, besides the binder jetting, they also work on some direct printing, like print those conductive wires onto existing object. They have such kind of machine, and I'm looking at their products because I really see some opportunity there for producing those functional objects, right? Because you could deposit wires or install some components during the printing process, which automate the manufacturing without further assembly or other manual work. Also, there are some other research, company like this object geometries, which initially started up in Israel and then got acquired by Stratasys. And they use photopolymer as the building material. But they're, all of these methods, they are based on very simple concept. That is, you use your building material and some binding agent to put things together, right? Actually, most of the approach, they are based on this so-called 3D printing. Actually, 3D printing here is not the one we used to use. Right now we used to use 3D printing as the general name for all the additive manufacturing process. But back to 90s, it is specific for this kind of jetting-based approach. And because it's kind of derived from the 2D printing, 2D jetting machine. So back to that time, this 3DP means the process similar as current like binder jetting based process. And this is introduced in 1992 by these two guys at MIT. And well, basically they claim this kind of approach is the farthest and the most cost-effective rapid prototyping technology. Because they use those powders, some plastic powder or some like those, I would say like clay powder for building the part. So they're not strong enough. So they're mainly used for the parts visualization, but not for some functional parts. And this method actually is built upon printing a water-based adhesive approach to selectively bond fine powders. Right, that is what we described previously. Just use the binder, which is some glue to kind of bind the powder together. And basically, utilize an inkjet machine to eject the bonding agents onto the successive layers of powder. So the binder is deposited in the area corresponding to the cross-section of the solid parts. So that is very standard for the additive manufacturing processes. And the binder holds the powder together to form a solid part, while the unbonded powders remain loose to be removed later, right? So basically, you just dig out the part you printed using this machine from the rest of the unbonded powder, right? So that's the nature of this process. But that suggests a kind of not a problem, but a step you have to do. That is, you have to clean up your part when you taking out the part from the powder bed. Right? So you have all those unbonded powder on the printed part. That's an extra step you have to do, and that really brings some difficulty to maintain the machine, and that's some extra cost. So here is another illustration on this process, right? So you can see the powder layer is deposited onto the existing layers, and then the binder will be added to the region of the layer, and then this mechanism will go further down by the amount of the layer thickness, and then another layer of powder will be deposited onto here, and then again the binder will put there. So on and so forth. You will have the full 3D object printed, right? Actually, I have one machine in my lab, but I never use it. It's a very old 3D system. No, not 3D system. It's ZCOP one. Yeah, it's a ZCOP machine. The major difficulty is here. Basically, as what we described in previous slides, basically you can only make things for visualization. It's so brittle. And besides the appearance, you cannot do anything to it. So, but based on this concept, as I mentioned in the very first few classes, there are some low-cost metal printing. They use very similar concept of this. Basically, they make their green part exact following these steps. But additional, they have a sintering process to melt the particle a little bit, to center the particle a little bit, to form a solidified part. And that's why this kind of process is still, well, on the hot spot. So it's not out of date yet because of this new development. They utilize the concept of this, and additionally add the sintering, and they use metal as a printing material. All right, that's some kind of extension along this line. And here gives you some idea about the printers like the ZCOP ones. I think actually they're not cheap compared to some fused deposition ones, right? The cheapest is still around 20,000 something, right? And as I mentioned, the part they printed is not strong enough. And but one benefit is easy to have this kind of full color printing, right? You can have really, very good appearance for the part, and the printing speed is pretty good. And also, because the material is just some plastic or other type of low cost material, so the total cost seems to be low, but you have the difficulty to do the post processing. So I don't know, after all, it's cheap or not, but if we just talk about the material, it seems to be very cheap, all right? So let's look at some videos. Let me share the video. Open this first. Okay. Stop sharing. Share. You can see this. This is a ZCOP 3. Oh. Oh shoot. What's going on here? 310. I'm sorry. But where it is, maybe I need to. Yeah, I think right now it's fine. All right. So, So that is how it looked like, right? And let's stop this and go back to the. I think I should stop sharing the sound. All right, and here shows more full color printings. Right, they look. I mean, they all look very good, but the only thing is the stiffness. It's not strong enough for functional parts, right? Yeah, but for some of the application like this kind of statues, right? This is called replicate yourself. Basically, you do a 3D scan, and then you just send your digital file to this kind of binder jetting machine, and then you will have a full color replicant of yourself. Okay. Right, and but that, I mean, maybe some people they have this. Yeah. And here's a report to kind of talk about this.
So is this the one early on you showed some slides?
Yeah.
For the first presentation that had like a human face.
Yeah. Yeah, exactly.
This is the technology.
Yeah, that is what exactly for that one. But for that work, the focus is they develop some computational method to reduce the requirement of the memories and computation, because you can see how detailed the surface is for the human. Right? So if you want to achieve such kind of such level of details, then you need to really consume a lot of computation and memory. So how to reduce that? Because if you infinitely increase the consumption, it turns out you can never process that. So that's why it requires some computation method to reduce that. But yeah, but you are right. That is made by such kind of process.
Yeah. Funeral home, you think that it also will turn your loved one's ashes into gemstones.
Well, right. I don't know how many people won't do this.
Yeah, William Lapierre is the funeral director that made the 3D printed scans of your loved one, and will also take the ashes of your dog or loved one and press them on the artificial.
I mean, I don't know for you guys, but
for the binder.
I mean,
you know what though? Here's the thing. The only reason people make it is because people will pay money for it.
Yes.
well, yeah, but I don't know.
I just see some rich guy collecting these, you know.
Even
I'm
I'm pretty sure. I'm pretty sure for Chinese, we won't do that.
Yeah.
If you do something like this, it's rather a curse than a blessing.
I agree. I like the photography there. That is on Photoshop. The way they put the figurines in front of the house and made it look like full scale.
Okay. Anyway, basically, just let you know what's the application for such kind of process. But yeah. Yeah. I know some people they print this for their wedding ceremony. Yeah. Put on the cake or something like that.
There's another guy that does the topography, so if you go on a hike, he'll print the hike you took.
Oh, okay.
So if you climb anything of note.
Oh, that's
I've seen a similar thing to this where they scan like real accurate, like Robert Downey Jr. or somebody. They'll scan the person, make a 3D printed copy of the person, and then all the hours that they spend doing costume design that they would normally have to pay that actor standing there, they use the 3D printed version. Of
that works.
Or whatever.
But my not argument, but my concern is how about just use the machine, sensing machine to machine. Well, why I ask this? Because I used to machine my own body as a mannequin. Because I'm not sure I show you or not, but I used to work on a program for wetsuit design, and I 3D scan myself, and I used the sensing machine to machine myself and put the wetsuit on it. I'm not sure which one is better, 3D printed or sensing machine it.
I would imagine you have a lot more ways, depending on the AM
Yeah.
technology, you have a lot more ways to
Yeah.
subtract it. You gotta start with a big cylinder or something.
Yeah, that could be one concern. Yeah, but anyway. All right.
I've seen heads machined like at the trade shows, but I've never seen a full body.
CNC
I
or?
did see a photo of like a woman or something.
CNC?
Yeah. Did they do that?
No, they-
this one time?
Yeah.
For CNC, you have to decompose. Decompose your body to several pieces. Because for some feature like the armhole, you can never machine it easily. So you just cut, and machine them and put them together. Probably you need to design some like this, like a snap fit or self-locking to put them together. Yeah. Let's continue. All right. So another similar process is called polyjetting. As you can see, there are some jetting heads which will move in XY direction, and some those powder or liquid drops will be spread onto this platform. There's my laser. Right, and again, this platform will move downwards, and another layer will be spread it onto it, and a UV light will be utilized to kind of melt the powder together to make them bonded to each other, something like this. And let's check another video.
Don't forget to exit full screen.
Oh yeah. I shouldn't. Oh. Where's my, okay, I need to.
PolyJet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. PolyJet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, appearance models, and master patterns. The PolyJet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. The data is then transferred to the PolyJet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the PolyJet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available through service providers such as Solid Concepts. PolyJet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. PolyJet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.
All right. So actually, the one developed by HP is based on similar technology. So but they gave a new name called polyjetting fusion or something like that. I don't know why they invent a new name, and they claim that is a new process, new category of a process. There used to be 7 categories of process, and they said what they invented is the new category. I don't know, but it seems apparently the surface finishing is pretty good. I used to check some of the parts, the demonstrate in on some conference, and seems to be good. Yeah, and also, yeah, the machine is quite expensive. Usually a few hundreds of thousands. Yeah, and I don't think it could. I mean, I don't know the exact number of for the thickness maximum, but I don't think it could be too large, right? Because you're yeah, it must to be thin, I think. Yeah, relatively thin. But the speed of this kind of printing could be quite fast, because basically the motion of this printing head could move very fast. Just similar to the 2D printing, 2D inkjetting, right?
There were a lot of heads there. Long. I wonder what the maintainability would be on.
Yeah. I start sad that when they showed all those little holes, that just looked like a nightmare to me.
Yeah. I'm kind of expect they have the similar problem of the 2D printer, the jams, or the material will start in the printing head and so on and so forth.
Yeah, we have one of these at Y12, and they have to. You have to time your build so that you'll be there when the build finishes. Yeah. So he'll set it, say, on a Thursday to start Friday afternoon, so it's done Monday morning when he comes in. Because he has to clean the head immediately. Or else
yeah, yeah, that's true.
Yeah.
So,
Ben Green has it in.
Okay.
Oh, object?
The big black thing?
Okay.
I didn't. Put the big table in there and Ben's office.
it looks like that big black one that they showed.
Okay, okay, I understand.
We never had issues with it clogging that bad. Unless you don't use it for a year and then, you know.
Yeah. But anyway, I think another could be a problem is for this kind of printer, you are highly relying on the supplier of the manufacturer. You have to purchase the ink from them.
And it's super expensive.
Exactly, just like the case of 2D printing.
It is very expensive.
Yeah, but for other printing process like FDM or even stereolithography, you could make your own material or buy some cheaper ones. But for this, I suspect you have to go with the original supplier. I mean,
not only that, the object company, the cartridges have chips on them.
Yeah.
With dates associated.
Oh, okay.
So you have to use it by a certain day or it won't even run on the machine. And users have gotten around that by changing the clock on it. You know, changing the clock. But
oh, that's
some companies don't want to do that.
okay. Yeah.
And it also knows which material you're using, because if your machine is not
Yeah.
rated for Vero Blue,
for the licenses.
Right, it's like, you have to buy a license
Yeah.
for a different material. It's like, just slap the sticker, get the RFID, put it on there. No, you can't do that.
Anyway,
Those
Yeah.
make very good looking parks though.
okay.
Yeah.
Oh, and the other issue with that is that the uncured material
Mhm.
is toxic.
Oh,
You have to typically get hazardous waste from streams established.
I'm hearing lots of reasons that it sounds like this would not be a good idea. I think it's a great idea. It sounds expensive. It sounds, in some cases, it's difficult to maintain. And you have toxicity issues with it.
If you don't work at a national lab, you don't give a shit about toxicity. Dump that shit in the river.
We had 1 hour of photo development at Walmart. This is not that bad. Trying to figure out where would this be used for?
The parts that it does make are really colorful, high fidelity stuff. You can also change like the hardness of materials. You can have like soft rubbery materials or hard plastic materials.
yeah.
This one, they, and kind of help me out here. So they made the Iron Man suit for Iron Man 2, I think, with the Connex, and then for remote controls. So for LG, they did a whole bunch of them so people could be like, hey, I like the way this one feels, because you could actually push the buttons.
It's more like kind of a front end.
The remote controls and e-bombs.
Yeah.
And they're starting to do like, is the they use the speaker, stuff like that. Colorful things like that.
I think one benefit for this kind of approach is it has high flexibility on the material and the colors.
Yeah.
Because basically you could just remember what we talk about this. Basically, they use the so-called voxel representation. They just discretize the virtual objects using very, very small cube. So you just imagine how you just continue increase the resolution of the cube. That means you decrease the size of each edge of the cube. Then you will have a very fine set of cubes. And you could, as long as this, the hardware support, you could accurately control the color and material property at each of the cube. So that really bring the flexibility to this process.
If I remember right, the object has 3 different materials, so 3 different colors that you can basically mix between the 3 to get all the ingredients.
Yeah, you have full color to use.
Yeah, it's like 25, 30.
Yeah. So anyway, it has pros and cons, but I don't know. Actually, HP is they said they are gonna launch another metal printer based on this kind of process. I suspect they must have some centering process after this. Yeah. Next year, in 2009, they said they're going to launch it. I don't know. All right, here shows some this PolyJet printers like the Object 500 and this Object 1000. And we can check a little bit on that. No. We need to stop this first. I think they take over the market quite fast. I mean, HP. They launched their printer in 2016, and I have some internal connections with HP Labs. And at that time, he told me he was worried about whether their printer is going to work or not. But surprisingly, they take over the market and
We're always striving to enhance the design process. We're always asking ourselves, how can we help designers convey their ideas, their creativity? It's our passion to empower designers with true design freedom, to help the most astounding ideas move forward. Connex multi-material 3D printing technology from Stratasys is our expression of this passion. Now, we've created a new 3D printer, the Objet 500 Connex 3, and we've radically enhanced the foundational elements of Connex technology to give designers more choice, more expression than ever before.
Connex technology has always worked by combining two model materials inside a 3D printer to create a variety of composite materials in one print job. With Objet 500 Connex 3, we've expanded the technology to let you start with 3 model materials, and for the first time ever with PolyJet technology, you have the ability to 3D print in color.
Colors with Connex 3 are vibrant and beautiful. You can pick from 10 color palettes for accurate, repeatable color with every build. You can mix colors with clear. You can mix colors with rubber-like. You can put 3 base colors into the Connex and build one model with 45 different colors. You can print digital ABS in the same model with rubber-like components. And you can do all this with PolyJet Technology's signature smooth surfaces for astonishing fine detail. Designers in the consumer goods industry, who are always improving on their last design, can integrate their innovations more easily than ever before and stay ahead of consumer trends. For important design reviews, Connex 3 will help you make beautiful prototypes quickly. You'll get accurate testing and thorough feedback before you go into production. You'll gain confidence with your ideas and wow your clients and focus groups with brilliantly colored concept models. You can increase your prototyping throughput by building models with a wider variety of materials and colors on the same tray. These new capabilities change everything. With the ability to print with 3 base materials, your creative possibilities increase exponentially. The Objet 500 Connex 3 challenges your idea of what 3D printing can do and what it looks like. We can't wait to see what designers do with it.
With the Connex 3, we can better duplicate the material properties of some of the things we're making.
It's important for our prototype parts to look and feel like production parts. In order to make the best bikes here at Trek, we need the best tools. And the Connex 3 is the best tool for the job.
All right. For the glass showing in the video, I have some more comments. Actually, I'm looking at some applications with additive manufacturing, and this customized glass idea came to my mind, and I did a little research on it. I think it has potential to be a good idea. Why? As I mentioned, the first step to start a customized design and manufacturing is 3D scanning. If for full bodies 3D scanning is really tough. But how about for face? Actually, I think it's much easier. And there are a lot of research already conducted to reconstruct 3D face from just a few images. Just one image in this direction and another one in this direction. And they just ask people to hold their credit card near their face. Why? Because credit card is in a standard shape and dimension. So they will take the dimension as a reference to measure the feature on your face.
Yeah, that's what they tell you. Then next month.
Plus, you get credit card numbers.
Make sure you have it faced where we can see the 3-digit code on your social security card in the other hand.
Anyway. Yeah. They could just take one picture front, one picture side, and then reconstruct your 3D face, and then adapt their design to your face, and then manufacturer send it to you. So I can see the whole kind of workflow for this idea. And there are some companies, startup companies, they're working in this area. So, because as we know, there are not much successful applications, especially for the consumer level market. Like we only have this teeth aligner and air bar. What else? Not much, right? So I don't know. Maybe we could have some new stuff coming out in the next few years.
Invisalign.
Yeah.
So,
No, they use the invention tech. They use the stereolithography. Yeah, that's faster. That compared this. Yeah. All right. Okay. I think we could have a break, 10-minute break, and then come. Yeah.
is Invisalign, are they actually 3D printing the aligners?
They're doing
Yeah.
the molds for their liners.
Every time.
Yeah.
So start off with what your teeth are, but then what your teeth want to be.
Yeah.
They do the 4-inch stuff and then they print them and then on the.
Yeah. Exactly.
Okay, because what I got from Invisalign is they don't print the aligner, they print the mold.
I think they print the mold for the aligner. not the liners
But
themselves.
they're still actually having to mold the aligner, not print the aligner.
I think
That's
so.
what I
think so.
But
I don't know.
I don't know.
I'm not 100% sure, but I'm pretty sure they just do the mold of the teeth using 3D printing, and then they actually use a
They
traditional
mail,
vacuum melt or something
Yeah.
like
Yeah.
that.
Yeah.
So I mean, it's like it's a casting.
Yeah, it's cat.
This filling through.
Yeah.
Might be good for you.
Well, even, it's easy sensitive, that's all right. You don't want.
Yeah.
Yeah.
One thing with the material from this though, it doesn't do well with the heat and humidity. It gets kind of
Yeah.
sticky and like it doesn't like melt, but yeah.
It's not good for using the south.
It's one of those things it's not a very good like engineering material.
Mhm.
It's not a permanent thing.
Mm-hmm. Yes. Well, that limits a lot of things. Yeah.
Yeah.
But for the glasses, definitely nylon could be one material. I'm
Yeah.
not sure whether this can do nylon or not. I know some of the FDM, they can do nylon successfully, and also the jetting, binder jetting,
Yeah.
they can do nylon, but I don't know whether this polyjet can do it.
Probably not, because
Not.
anything it's a photo cured
Yeah.
resin
Yeah.
that it uses.
Yeah, yeah, the material is.
Think of it kind of like SLA, but instead of having a layer,
Yeah,
of
yeah,
curing
yeah.
it, you're
Exactly.
basically just shooting it and then curing it.
Yeah, that's true. Yeah.
This is the end of your MATLAB simulation of your yeah. For the most part, you can probably copy and paste a lot of what you did like robotics. That stuff.
Yeah, sort of the code, rotation stuff is the same, translation stuff is the same.
Just make some models.
Try to envision what the hard part would be. I think I could make like a curtain being scanning thing that rotates, maybe like slightly translucent. I think the part I'll probably need to think about a little bit more is
Yeah.
Making it move and do those things shouldn't be that hard.
If anything, maybe like do the basically you have like a point cloud, big matrix, and go move your whatever your set is from each of those point clouds or something.
Yeah, it depends on, I guess, how complicated the shape is. To make a rectangle or something.
Yeah.
Like this animation, just do that and go up to the next.
So to believe we're already at week 7.
Yeah.
Because ultimately, whatever machine this would be, we control something. So
Yeah,
that
yeah.
situation where getting in coordinates.
Yes. Look like MacBook. Summer semester is fast. It's much shorter.
Yeah.
Yeah. It's already the sixth week. And
Does Tennessee Tech do like split summer classes? Do you like first summer and then second?
yeah, it has.
First, second were full.
Yeah.
I only did, until we started doing stuff here, I only did one summer course. One semester where it was at MATLAB for the whole summer, and then there was something for the first part, really fast.
Yeah.
Like it was over in no time. Yeah. It's like, this is the introduction. All right, completing that today's class.
Yeah. Yeah. I remember when I was taking summer courses in Charlotte, they split up that first summer, second summer, entire summer.
Yeah. So I generally try not to do summer classes.
Oh, okay. So you graduated from UNC Charlotte?
Yeah. Yeah. Myself and I graduated about 3 years ago.
Okay.
Kevin graduated there like 15 years ago.
You're really in the same age.
Yeah.
And I've been there at UNC Charlotte once. Last 2007. Actually, I had an interview there.
Yeah, there's one professor there, Jeff Burkay, who does additive manufacturing stuff. But for the most part, most of what they do is, precision metrology.
Yeah. They have a strong team on the measurement, precision manufacturing.
Yeah. We had a couple, like every semester of undergrad, we had some, or every year of undergrad there was a design course.
Oh, okay.
And our junior year design course, we had to do whatever makes a robot or something. We had to incorporate at least one additive manufacturing part in there.
Yeah.
Yeah. A few FDM machines. I don't remember if they had anything else. But at least had a small lab.
Yeah.
Several FDM machines. Sure, they probably worked with 3D systems at some point in time. 3D systems is less than an hour away.
Right. There's exactly.
They're just over.
They're North Carolina or South.
3D Systems is in South Carolina, and Rock Hill, so the bottom edge of Charlotte is on the North Carolina, South Carolina border.
Yeah.
So like a quarter of Charlotte is actually in South Carolina, and that's where Rock Hill, South Carolina, is where 3D Systems is.
Yeah.
So they're right just below the border. So it's like a 45-minute drive.
It's pretty nice campus. Actually, I have interviewed with computer science, not mechanical. As you can see, the nature of my work is multidisciplinary. I did a lot of computation.
So you probably went to the big Epic building?
Like a regular job. Yeah. Somebody else supporting you. Oh, I got a Jacob today.
Yeah, their electrical program does a lot of like power generation stuff. Duke is their big sponsor.
Yeah, that's very good.
And also you have there's some financial
Bank of America.
Yeah, exactly. So some people, some faculty just work on the
finance
or security.
Yeah,
cyber security. Okay. So we're gonna have another assignments. So that's it, only two. And then I want you guys to focus on the project. It's already the 6th week. So we only have 4 weeks left.
Time flies.
Yeah. That's incredible.
We'll be swamped with homework from Chris Wilson in no time.
What did he talk?
He's doing a like an engineering mathematics course for us.
Yeah.
However, there's some of us that are open to take a different class. There's one being taught.
I don't know if we can weasel our way out of this one.
I'm weaseling my way out of anything. I'm not
This
taking
time.
So what that class about? It seems to be a undergrad level class.
So most engineering programs typically require like a 5,000 level math course.
Oh, okay.
So this is basically a version of a 5,000 level math course, but not by the math department.
Was it gonna be 6,000?
I think technically it's a 6,000 class, but usually every grad engineering program requires like a grad level math class. It's basically a version of that.
We've had 3 grad level.
Engineering analysis class, so it goes, you know, like with exact solutions and computational solutions.
Oh, okay. Okay.
It's more of an applications of mathematics.
Oh, okay.
Yeah.
So you use MATLAB?
Probably it's an ANSYS.
ANSYS.
If I know Chris Wilson, he'll.
Yeah.
There'll be some finite element.
Yeah, he's
a
a fun guy. Yeah, he's from Boeing.
So
Did a lot of analysis.
So we dropped the answers.
It's not giving class anywhere.
The company dropped the answers?
Company decided to drop the answers. Not something. Such a thing but we fought for that. Oh, answers was starting at like $60,000. Maintenance of all of the modules.
All the packaging guys use all those modules though.
Used, yeah, but they were told they can't use them anymore, so we can't certify any package.
I'm sure that's going over very well.
There's no new packages in design.
Yeah.
That was, I mean, we went up and validated answers for the good drop-in packs and all that stuff, and now it's just.
That was the word. Just, all I needed was fiber drums to ship parts across the plant. And I had to go through packaging.
The most expensive fiber drums in your life.
Yeah. it took like 3 years to order, you know, 2 fiber drums.
Yeah.
Come on.
So we've been working for a year to order 6 indoor drums.
All right, let's continue. So I probably will skip this video. Basically, it gives you some idea how large the part could be printed using this PolyJet printers. But similar concept of the printing process. So nothing special here. And there's a very important kind of feature of this kind of process you have to look at is the droplet formation, right? Basically, all the material is spreaded by in the form of droplet. And there are 2 different modes for the droplet formation. One is the continuous mode, means it's a continuous flow for the material. Another one is the drop on demand mode. So basically, you can just consider about those one drop. I mean, you can just consider about the material will be spreaded by the discrete droplet. So here gives you the differences. You can see how the distance between each for the drop is larger for this drop on demand mode compared to the continuous mode. Right? So there are different ways to kind of control this droplet. You could use thermal energy or piezoelectric method to control this droplet, and I will introduce some details later on. So for the continuous mode, you have all these setups, right? Basically, the fluid supply or pumper will pump those droplets, and these droplets will be charged through this charge driver. And then you have this deflection plates to apply, to kind of guide the path of the droplet. And you have this droplet catcher, and then finally this droplet will be put onto this substrate. And you can see the distance between each droplet is very small, and you could consider about as a continuous flow. But for this demand drop-on-demand mode, you can see the setup is much simpler. And from this fluid supply, the droplet is formed and then controlled by certain mechanisms, and then put onto this substrate. And you can see this substrate is in motion such that you could have your droplet is placed in different location. And the distance between each droplet is relatively larger compared to this continuous mode. And there are different ways to control this. And also there are some kind of quite new research. They are trying to control the shape of this droplet such that what you printed will have different surface finishing. And basically they build up a relationship between this shape of the droplet versus the voltage to control the formation of the droplet. And they use some machine learning based approach, and they successfully get some insight that maybe certain shape like ellipse, solid shape, or some sphere shape will give what kind of surface finishing. They successfully establish this relationship, and then they will control how the droplet is formed, and something like this. That's why this kind of a drop-on-demand mode has flexible controllability on the surface finishing, because you can precisely control each of the droplet compared to this. All right. So there are different ways to form a droplet. You have the thermal or piezoelectric method. So basically you put a heater here, and by control how much thermal energy you applied, you will have all different droplet formed, right? And so same thing happens to the piezoelectric based formation. You have a piezo ceramic put in here, and this piezo ceramic could be deformed when you apply certain voltage on it. And how much it deformed will control the shape of the ink, the droplet to the shape of the droplet, all right? So that's the two different ways to control your droplet. And okay, that is for the polyjet printing. And all right, let's move to another printing process, which is the selective laser sintering. And this is introduced in 1988 by Carl Deckert at UT Austin. And every year there's a additive manufacturing conference called Solid Frame Fabrication, which is located at UT Austin. Basically, when I first came to there, and they mentioned, okay, here is the place where we invent additive manufacturing. Because at that time, I was not familiar with selective laser sintering. So I was shocked, what? Because what I know is fused deposition modeling and stereolithography, and they are obviously not invented at UT Austin. Then I look at this method, okay, oh, I know. Basically, they claim this method is invented there, and that's why they said UT Austin is the place where additive manufacturing is invented. But anyway, just little history. Okay, so this kind of process is also based on the powder bed, right? And they are marketed by the DTM Cooperate, and right now the DTM is acquired by 3D Systems. So this selective laser sintering has a relatively wide range of powder material. They could they could make parts with polymers, metal, or ceramic, or even some composite material. And recently they use sand to make some glass-like shape. But same concept, same way for the process. And this process is based upon the use of laser, which provides heat to melt and center powders into solid. Based on how much power is used, you could fully melt the powder or just do a center ring of the powder. But it's quite similar. So this is a kind of illustration of selective laser sintering systems. And here gives you the laser to sinter or melt the powder. And there's an IR heater to help this sintering process. And but for this leveling and this mechanisms for moving downwards is quite similar to the binder jetting process, right? Basically, one layer is centered, and then this leveling roller will spread another layer onto it, and then the new layer will be centered or melted. So, but this power source is much higher, right? And also they can really produce some object with high stiffness, like those ceramic or metal parts, right? So you can see what are the main components for a selective laser sintering systems, right? You have a laser source and optical part to kind of guide the laser to certain region. And you have a chamber to process this melting procedure. And this roller mechanisms will realize the new spreading of a layer. And of course, that could generate some environmental hazards. So there will be an environmental control unit, right? And these two powder feed mechanism and part builds mechanism are quite similar to what we described in the binder jetting process. Of course, you need to have softwares to control this whole process. So this is a whole loop for a selective laser sintering machine. So some characteristic. A moving laser beam centers heat fusible powders in the area corresponding to the CAD geometry. Basically, once you have one layer of the object, you can just use the laser to center it. After each layer is completed, a new layer will be generated by spreading the new material onto the existing one and then do the centering. So in area not centered by the laser beam, the powder are loose and can be poured out of completed part, just same thing as what we did for the binder jetting, right? Here gives you some examples of the selective laser sintering systems like this ProMaker P1000 machine. And we can look at a video about it. Okay. Did I share the sound? Yeah, okay, did it.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures.
Artistic structure.
Okay. So any comments or experience with SLS? Actually, I have one question myself. In the video, it mentions it does not require support material for SLS, but I do hear some other things that it does require support material for some metal things or some other parts.
I would imagine there's only certain geometries you can do or certain overhangs or something.
Yeah.
Because a solid powder, as long as the powder is strong enough to push away, you don't put the energy over. But I have a hatred for SLS.
Yeah.
People don't pay attention to material properties of powder. So some of it's toxic, some of it's explosive, some of it's fire.
Yeah.
People have caught a lot of those machines on fire.
Yeah.
So on the leading edge, on the bleeding edge.
So this is the
We have
sintering process. This is not the melting process, right? This is the sintering.
Yeah.
But does this SLS encompass both the main?
I think no. There's a selective laser melting. So that is melting. Oh, so melting requires support.
Yes.
Oh no. Oh, it requires. Oh, that's why. Oh, I got confused on this. I see.
You're never melting the powder, so you got all those particles that are sticking together. But when you melt it, like this, if you got nothing under it, it just winks down into the powder that's below it. So you have to have something under it.
Okay. Makes sense. Oh, that means.
You can have a lot of work that you have to do manually after that. You can clean all the powder out and then put it back.
Some of them are automated. They touch the powder out and bring it back to the pump. But yes, it comes out very rough. That's have all these little spumpy and everything. You're not careful. And you'll notice now everybody's wearing less all the modern videos. The first videos that weren't, okay, you're dead.
So it doesn't seem like it's like a production level application with all of that whole process.
There'll always be a break even somewhere here.
I don't know, we printed drones, we printed all sorts of filters,
and those people don't have to be machinists in the industry. Those are.
Oh, what I'm saying though is that, I mean, at some point you're gonna just pay for your injection mold and you just put it in the machine and run it.
Of course.
take the optical parts away and put them on the market.
But it's great for the 999 light bulbs.
Okay.
It's not good for the.
Yeah, it takes 6 months and $100,000 to conventional. So we can make one, something like this, and have a quick answer and feedback.
Yeah.
Sure, I understand for rapid prototype, but I'm not saying it does not look
Full blown
like
production.
like a production ready unit like they keep telling me.
Oh, no, it's not. Yeah, there's a lot of things, and companies are coming out with improvements to the machines, like the Concept Laser X-Line machine is a gigantic powder bed metal machine. It's got 2 chambers, so like to deal with the powder, harvesting your part out of the powder, like the thing just rotates, and so you get a new build, you can start printing on the next print while you're over there digging your part out. And there's other ones that focus on more automated powder. There's even some that are like partner based.
They've used SLS to make guns and silencers. So it's actually strong.
Yeah, I've had experience using this. I did a design project in school for IndyCar team, and they, for their wind tunnel testing, they made components SOS and stuck it in their half-scale wind tunnel at 100-mile-per-hour wind.
All right. Okay, let's move on. So as you can see, the softwares for an SLS systems is quite similar to the one for SLA, but there are some key differences. First is the heat control, right? Because you can see there it involves a large amount of power, laser power, to center the powder. And another difference is it does not require support material, so you don't necessarily to generate the support for building the part. And but other than these, it's pretty much same, right? Very slow for the software.
Well,
Software.
everything.
Everything. All right. Yeah. Okay. Good. So here shows some polymer parts generated using this SLS process, and also some metal parts like this one, but I don't think the left one looked like a metal. But anyway, the right one, pretty much a metal one. So here gives another example. Basically, it's a cage that was used for 3D system to demonstrate the toughness of their printed part using this SLS. And you can see the wire of the cage are 1/4 inch in the diameter. So basically, they put on a full-size 3/4 ton Chevy truck onto this printed structure like over here, right? And it's very tough. So you can see it can successfully hold this amount of load without cracking or broken, right? But after all, it's not metal. So for metal, it could be totally a different story here.
That's a distributed load. Come on, that's not how you gonna rate. It's 3/4 pellets divided by 4.
Yeah, I mean, there's street performers that do that.
Actually, I know some artists in China. They use this SLS machine to print some jewelry, in very complex geometry, and they're selling their products to those people who are interested in some new stuffs other than the conventional made jewelry. But I don't know. I'm not sure how large the market size is for this kind of application. But apparently they are working on that. So the primary binding mechanisms in those powder bed fusion-based methods will be these 4 different categories. So there are some solid state sintering. There is also chemical induced binding, and also liquid phase sintering. And the last one is the full melting. So yeah, and we can take a look at what they are. So for the solid state sintering, basically it's the fusion of powder particles without melting, right? So it occurs at a temperature between 1/2 of the absolute melting temperature and the melting temperature. So the driving force is the minimization of total free energy, which is proportional to the total particle surface area. So you can see from this figure, here gives you the unsintered particles. So they're not merged together, but after you're applying certain energy there, and they become, they are centered together, and you can see those area, those hollowed area, I mean, the space in between of these particles will be decreased to a certain level, and that is the solid state sintering. Some chemical-induced sintering, so it utilizes the thermally activated chemical reaction between two types of powder, or between powders and some spherical gases to form a biproduct which binds the powder together. So the fusion mechanisms is primarily utilized for ceramic materials. So here gives you some chemical formulation which indicates how this kind of a reaction happens. Right? You can see how these ceramic powder work with the oxygen and also some other gas together to complete this sintering process. Now the liquid phase sintering, so it's also called partial melting. So it's the fusion of powder particles when a portion of constituent within a collection of powder particles become melted, while other portions remain solid. So it's kind of in between of sintering and melting, fully melting. So the melting constituent acts as the glue which binds the solid particle together. And high temperature particles can be bound together without needing to melt or center those particles directly.
Is this going to be two different materials then, or could this be all the same material?
All the same material. And you can see from this figure, here shows the original states of the particles. They are separate, right? And then you can see the composite particles, and they are coated onto this separate particles, and they got mixed together to bind each other, and that is the liquid phase sintering. So the last one is the full melting. So it is associated with the powder bed fusion process of engineering metal alloys, and you can see all these alloys could be utilized as a printing material, and also some semi-crystalline polymers like nylon, polyamide. So the entire region of the material is melted to a depth exceeding the layer thickness. So, the point here is the material particle will be fully melted in this case. And so for this kind of process, the common challenges will be the powder handling challenges, because you have all the printing material in the powder form, right? So the characteristic of the powder delivery system should be something like the powder reservoir of sufficient volumes, and the correct volumes of the powder must be transported from powder reservoir to the build platform. And the powder must be spread to form a smooth, thin, repeatable layer of powder. The powder spreading must not create excessive shear forces. Actually, there are some researchers, they just focus on to the characteristic of the powder shape or the size to make sure this powder will give these kind of process the best quality printing. And they are trying to form some computational model to link this powder size shape versus the surface finishing and material characteristic of the printed part. But it's still in the, I would say, there are some good results coming out, but I cannot see the full solution ready yet. And there are still a lot of work to do. Other researchers, they are just work on the thermal control of the melting pool. And they are trying to figure out which is the control mechanisms for the temperature during this melting process. But another difficulty is the basic physics of this process. It's not that clear yet. And actually, that's the one hot area people are looking at. And those federal funding agency like NSF, they really found a lot of research in this direction because it related to those industry level production, and especially they could be used in the aerospace and also some military applications. So, yep. So some other challenges, the universal characteristic of powder feeding. So small powder particle size enable better surface finish, high accuracy, and thinner layers. However, this will cause some problem if the size of the powder particle is too small. So if the size decrease, so the interparticle friction and electrostatic force could increase. So when the surface area to the volume ratio of a particle increases, its surface energy increase and become more reactive, avoid burning and explosion in the presence of oxygen. And also small particles have a tendency to become airborne and float as a cloud of particles, which may cloud optical, reduce sensitivity of sensor, deflect laser beam, and damage moving parts. So all these challenges actually motivate people to work on, as I mentioned, the characteristic of the particle size versus the final products. The final products quality. And yeah, it's still challenging. So the feed carriage and the counter rotating roller will also have some problems. So the counter rotating roller creates a wave of powder flowing in front of cylinder, and the counter rotating roller pushes the powder, fluidizing the powder and making it more flowable. Shear force created by the counter rotating roller are small. And all these problems are caused by the mechanical motion of the roller, which is part of the printing systems. And but it also essential to the final printed parts. And also some issues about the Dr. blade. So the ultrasonic vibrations could be utilized to help the fluidize of the powder. And so these are all factors when we talk about the feeding of the powder. And all these factors could affect the final printing surface. But again, it's a very complex problems, and it has multiple variables, and how to model the physical behavior of this. Yeah.
I would think that, I mean, maybe I'm wrong, but I would think that you're pushing right up to almost all of the same challenges that you have with traditional casting processes. you have melted material, you're in that region now.
You're way worse than that. There's a lot of variables.
I mean, with all the additional complexities. So, but you have a lot of the same design limitations that you do with traditional metal casting processes. So,
much higher.
So I would be thinking that, they're going to have to overcome a lot to do any better than the current casting process.
Yeah.
And actually, there was an AM conference in Knoxville a couple of years ago, and one of the presenters was a guy from the casting industry, and his whole presentation was, "Oh, look at this really complex part. Yeah, we didn't make it using additive. We made it using casting. Oh, look at this other really complex part." So you say, "Hey, you guys think you're making these really fancy parts, but I can cast these same geometries." So there is a decision that you got to make in production. Every part too,
Yeah.
Use this or not.
Actually, I'm wondering, do you guys, have you guys been aware about the mechanical properties compared to, the differences between the parts generated using this kind of additive and versus the one generated by casting? So on and so forth.
Yeah, that's the number one limiting factor for why we don't have a lot of AM tools.
Yeah.
Yeah. We're carefully select which application.
Yeah.
This application.
Oh, that one broke. That one broke.
So for a
this one didn't break.
So for a vacuum pod, you can make the vacuum pod really good, but as soon as you put a lifting lever on it, now it's a lifting fixture, right? That would have to be evaluated. You have to know the properties of that thread pull out, and that gets really complicated.
Well, in that specific case, it's itself not a lifting fixture. The island. So you could calculate your way through that. But for say a lifting device, right? If you wanted to make a lifting device that picks up parts, yeah, you're bounded by codes, and the lifting device code requires that you have material. You design your fixture of materials that have properties that are agreed upon by consensus standards, and there's no consensus standard that say you have this minimum tensile strength for some AM process right now. Because there's so many variables that go in.
It's vacuum when you put lifting on it, it's still lifting.
What are you picking up?
Vacuum.
Oh, you're saying that? Oh,
You're picking
you
up.
said a machine pod.
No.
Oh, vacuum. I'm sorry. When you said vacuum pod, I was thinking like a chuck.
Yeah, but as soon as you
Okay. Yeah, if you're designing a flow lifting device, absolutely.
kill the smalls.
On the same page.
Yeah. Yeah, I think one big concern is because the way of additive manufacturing, it probably has better mechanical property or tensile properties in one direction, but not in the other one. Along the direction, it should have. I don't know. It's supposed to have weaker the tensile tensile property than the one in XY direction. Is it true? Always true?
No, it depends on build orientation.
Building orientation.
Right, yeah. But if you're building up in Z, that's the weakest direction.
Then it's SLS or SLM. That's SLM.
Okay.
Sure.
So the SLM will really give you better, much better.
More uniform.
More uniform.
More uniform,
Z
okay.
gives you weird profile.
Oh, that's
Because you can't control where it's going.
yeah.
The spread. All right.
So what you do, with every part, you print a little tensile test coupon right next to it, and
It'd go.
There's been talk about
but that even doesn't give you all the answers because you get different properties.
Changes
based on
where your location.
On the plane, you get different properties based on how thick your plane.
So you print a tensile test specimen all the way around the outside of the part and some of the inside of it.
But if you've got something that requires 100% testing, it doesn't matter. So there are certain things that once you follow the code, every item's going to be tested. So you might as well use that.
Yep.
Yeah, that's probably the biggest challenge for any of this.
All right, let's move on. So here gives you some illustration on the powder handling systems, right? You can see these are all the elements we mentioned in previous slides, which part the hopper, the duct blade, and also where the platform is. And so how the roller spread the new material onto the existing layers. And all these elements could be a reason for certain behavior of the final product, right? So also there are some here gives you some description on the metal or ceramic part accretion using those powder bed fusion approach. So as you can see, first of all, the powder are loosened, and then after applying a certain fusion process, it becomes green part, right? Usually and then the brown part will be something like this, but after further centering or melting, you will have the finished part with much dense, much high density compared to the loosened part. And this kind of process actually gives you the basic concept for many of the new approach, like the one desktop metal did. And also there are some stereolithography based approach. They could build ceramic part, just use similar concept. They use those polymer binder to band the loosened particle together, and then go through all the following process to solidify the parts. And yep. So, and there are different variations for this powder bed process. And they have different delivery method, heating process. Energy could be different, right? You could use the laser or even electron beams. I will introduce a little bit the electron beam based method. Also, whether you make it vacuum or you put some gas there, right? And the optical devices could be also different. Right? So the laser-based systems also could be used for some low temperature process. And low temperature, those powder-based bed fabrication machine fusion machine are designed for those direct processing of polymers. As we did introduced, the SLS could be used for building those parts with nylon powders, right? And some low temperature powder bed fusion machine are designed for indirect processing metal and ceramic, like this kind of direct metal laser sintering, and also the one developed by the desktop metal. So also some liquid phase sintering of special alloy mixtures. So you can see all the different variations for laser-based systems.
When you say alloy mixtures, again, same question. Is that two materials or is that one special alloy?
Oh, you mean this one? Yeah, that's the mixtures.
That's two materials.
Yeah, two materials. Use some liquid agent to bind together and then go through some sintering post-processing. Yeah. Yep. Here gives you some companies who are working in those low temperature direct melting and sintering process for metal or ceramics. Also, another quite popular process is the electron beam melting, right? So this process is developed at at Sweden, and it is commercialized by this Arcam AB company, and basically it's quite similar to the selective laser melting, but it uses a electron beam as the the power source, and it is in a high vacuum environment, other than an environment with the gases, right? And so it can build those stainless steel, titanium, and other metal parts. So it's because for those medical implants, they usually use the material which the electron beam melting could process. So it's very good for this method to be adopted in these applications. But the drawback here is it is very expensive, right? And this gives you some comparison between the EBM versus SLM. So you can see first the thermal source are different, right? One is electron beam, another one is laser, and also the atmosphere, one is high vacuum, another one is some gas, right? And the way of scanning, energy of absorption, also quite different. Also, how to preheat your powder. There are also differences. For the electron beam melting, it uses electron beam to do the preheating. But for the selective laser melting or selective laser sintering, they all use the infrared heaters. For the scan speed, the electron beam melting has a very fast scan speed, and this is magnetical driven. And but the laser melting is limited by this inertia. Yeah. Compared to the energy, apparently EBM has less consumption compared to the selective laser melting. But for the first is finishing, actually I'm not sure whether this is true or not, because I saw different things about this surface finishing. And some prefer the electron beam melting than this selective laser melting. But according to this book, actually I got this from a book. It says the selective laser melting is better. Generally it's better. And for the feature resolution, it seems selective laser melting is also better. For the materials, because this EBM utilizes the electron beam as a source, so it has to be a conductor. So only metal could be used for the building material. But for the laser-based, polymer, metal, and ceramic are the material could be used. So any comments on this comparison or features? Yeah.
The other thing about electron beam effect have mass loss, vaporize deposits.
Okay.
That's the only other thing. You don't have much mass loss.
I see.
You have 3% mass loss.
I see. Okay.
How do you remember this stuff?
He's Dougal.
Yeah, because personally, I didn't use either EBM or SLM before. I used a little SLS machine, but I never used these two.
So the material properties better with the EBM or SLM?
We can control the heat effective zone with the, the other thing we're doing with the other thing we do with it is put in different powders. You can mix your metals. You don't have to use different metals. And then it melts them all together. You can't do that with it.
So I assume the power, I've never seen the infrared heaters. Selective laser, but I guess that's a way of them heating the next layer of powder. I know in the electron beam, they do that with, like it says here, the electron beam. But I imagine you can get a lot more power out of that electron beam and infrared heat, a lot more heat.
Oh, you mean this preheating?
So when they do that preheating too, that the ones I've seen, they actually partially center the entire bed.
Yeah.
And so then you know when you get your part out, it's not loose powder anymore. It's
Break those
chunks. Yeah. And so from like a powder recyclability standpoint, that would be less desirable because it'd be harder to get back to that original powder.
So that's a drawback actually. You mean this?
Well, it's good though too because you get less of a delta T when you're building your parts. So you get less thermal warping and thermal stress.
It keeps everything warm.
Yeah, I see.
Closer to the melting.
Yeah, I understand. But
What you want, what's your desire?
Exactly. Actually, to me, one thing I don't get it. Yeah, well, I'm sorry. Yeah, one thing I don't get it is it seems the SLS has better properties in many of these aspects. Then what's the necessity for EBM? Why are people still developing this?
Very
controlled.
Yeah, it's in a vacuum. You know, so the heat that you put in that part stays there. Part stays very long during the whole build. Whereas the SLM, it cools, it like quenches every year. You know, and so you build up all the stress. You know,
okay, I see.
And the higher the vacuum, the better.
Yeah. Okay, that makes sense too. All right.
In fact, about E-beam, I don't know if anybody's seen them, but the light bulbs that they put inside, so you can see, they don't need the glass dome for the light bulb. It's just two filaments because you've already got your back.
I see.
And there's no glass on the bulb.
Got it.
They just do that.
So the scan speed is very, very, very fast. But how quickly you can achieve vacuum is dependent on the built in.
How's the spot size for like the a lot smaller than laser?
Or not.
Yeah. I kind of figured.
I see.
And isn't the scanning faster on the E-beam? I think you can
you
can deflect it instead of it being one spot that has to raster everywhere. I think you can spread it because it's got so much power. You can spread it too.
I see.
It's a bigger area.
Makes sense. All right. I think here shows some examples for that. I will skip the video. You could check it later yourself. And okay, let me finish this. Maybe use a little more time. Finish this whole PowerPoint. So there are different ways for these either laser or E-beam to kind of form the patterns. There could be some mask-based centering by utilize the mask to preheat center the powder before you use it, or you could use some inject printing-based method to center it in the layer in line-wise, right? And or you could use some other this layer based way to do the centering for the powder for the powder.
Isn't that the one we watched the video on? Didn't they use that in one of the videos we had where it showed?
Yeah, that is what
that process.
Yeah. You mean the
inhibitor, the centering inhibitor.
Yeah, you mean the polyjetting.
Desktop mode.
Desktop mode.
You're thinking of desktop model where they use core material. They use it kind of like core material because it breaks away, so because it doesn't actually bind.
Yeah. All right, that's all for today's class, and we are gonna talk about more next. This Thursday. All right, and okay.
cool.